screen now?
Yeah, I can see it.
Okay, so 3.1, 3.2 should be relatively straightforward. How do you feel about 3 and 13? Like, are they good, bad?
I think it's okay, yeah.
Okay, all right, well, we'll just go through this and we'll see if there's anything that's missed, and you can ask me any questions. So it just starts off with the periodic table basics. So this is just terminology stuff. So groups are the vertical columns in a periodic table, so they go downwards like this, and the periods are the ones that go across. And the numbering for groups goes from 1 to 18. There are some periodic tables that number it 1 to 8, and so they skip all these middle bits. Oh, well, they do 1, 2, and then they just put 3, 4, 5, 6, 7, 8. That's not the numbering that the IB uses, though, so don't do that. Just do 1 to 18 like this one does it. And yeah, periods go from 1 to 7. At least those are the ones that we're concerned with, because technically there is a whole, this section, which is like taken out from the periodic table, like a normal periodic table, just has it at the bottom, because this is the long version of the periodic table. But you don't need to worry about those. And so this diagram here, if I get rid of all these lines, basically tells you the properties of all of the elements that we have. So this is all of the red ones are nonmetals, and these green ones are metalloids, and the yellow ones are metals. So there's quite a lot more metals than non-metals from this diagram, and that's just because of the definition of what a metal and what a non-metal is. And this is another way of illustrating the periodic table when you have this lanthanoid and actinoid section actually put in. So this is what a normal periodic table looks like. Sometimes they separate this section outwards though, so that it's easier to fit on a page. But yeah, so these names you should already know. So group 1 is, group 1 is your alkali metals. And the reason we call them alkali metals is because, like, once you get to topic 8, you know that all of those metals in group 1 will react to form bases whenever they're put with water. And another term for base is alkali when you're reacting something with water, which is why they're called alkali metals. Group 2 is called alkaline earth metals because they also form basic solutions when they're combined with water, but I don't really know why they're called earth metals, not really my problem. Transition elements, we're going to cover those in 13.1, I think, and they have specific, their own like characteristics that we can discuss then. These groups don't really have names because they're not that important. And then halogens are everything in group 17, so they only have one valence, like one unpaired orbital in their outermost shell, so it's completely full except for one, is all the halogens, and the noble gases are considered noble because they, what on earth? Can you still hear me?
Yeah.
Oh, something just went weird. Okay. And the noble gases are group 18, and so they've got a completely full outer shell. It makes them inert, but not completely inert. So you can actually react ones like xenon, xenon and radon, especially like these bottom ones, because they get a bit more unstable because they've got so many electrons that you can just about force it to react with other things. But naturally it doesn't want to react because it doesn't need to. It's already got a full outer shell, so it's already completely stable. What's this? Okay, this is just to do with metallic properties of substances. So metallic properties are related to ionization energy. So if you're a metallic sort of structure, that means that your ionization energy isn't really that high, because what a metal is something that when it's bonded, it's just a bunch of positive ions, and then there's a sea of delocalized electrons around it. That's probably the terminology that you've heard. So there's just electrons, which are these tiny little things, that don't belong to any particular nucleus, but they just swim around the place. And so a metal has to be a substance that can let go of these electrons rather easily so that they can form this sea, which means that their ionization energy is usually pretty low. And here it just says, these are just the properties of metals, like within this metal block that we talked about before, this whole entire chunk. So as you move across the period, like rightwards, the ionization energy increases, which means the metallic properties diminish. And you can see that here because you start off, like if I use period 4, for instance, I start off completely with metals, like on the left-hand side of the periodic table. It said the ionization energy increases as we go along the period. So when the ionization energy is low, that means it's more metallic. It has more metallic properties because the electrons they can leave the atom easier to form metallic bonds. So on the left-hand side, it's mainly metallic properties, and hence they're metals. But then as you move across and that ionization energy increases, so basically the energy required to remove one of those electrons gets higher, then it starts to lose those metallic properties. And so you get metalloids, which are sort of metals, but also not really. And then that ionization energy increases so much so that it's basically not even a metal anymore, which is why we call them non-metals as you get all the way to the right-hand side, which is why all of these are non-metals and practically all of these are metals. So that's just the way that the periodic table is organized, and it's a handy thing to know. And that ionization energy increases because you're basically filling your outer shell, and so the atom's starting to become more and more stable, so it doesn't want to keep on giving away electrons. So that's why that property occurs. But it's that's one that's good to remember. And another one is as you're going down a group, the ionization energy decreases. And the reason for that is as you go down a group, I mean, I'm sure we're going to go through all of these in 3.2 because that's all the periodic trends. But like if I'm in like period 1 versus period 5, where I've got 5 shells, I'll just draw 4. So let's say I'm in period 4, period 1, period 4. If I have an electron that I'm trying to remove from the outermost shells of each of these, it's much harder to remove this one than it is to remove this one, because this one is further away from the nucleus. And so this attraction is much less than this attraction because they're further apart. So remember, the further apart your electron and your nucleus are, the easier it is to remove it. And hence, if it's easier to remove, that means that my ionization energy is technically lower. And so if it's lower, that means that it's easier to have metallic properties, and hence your metallic properties increase as you go down a group. And we can probably see that if we look at group 14 here, which I'll do in like a different color. If you look at group 14, you start off with a non-metal, but then, as I said, as you go down the group, your metallic properties increase, and so you're non-metal, and then you become a metalloid, and then you've got full metallic properties, so you've got these metals down here. So that's just some information about how the periodic table is organized. It can probably help in paper 1 when you're just given a periodic table, but you're not told, like, it's just that blank periodic table that you're given, which just has the name of the element and its atomic number. So you sort of have to use your own like prior knowledge to be able to figure out what's what. But yeah, that's the basics about the periodic table that you should know. Is that all good?
Yep, that's good.
Okay. And now what is this? Electron configurations. We already went through this last topic. Yeah, there's nothing special there. This is just some terminology here. So what a valence electron is. So it's just, since chemists always refer to the electrons in the outermost shell of an atom, like they're like the most important things in terms of bonding, we give them a special name, which is valence electrons. Nothing too fancy about that. But yeah, that's 3.1 done. So now it's this chapter, which I don't like at all, which is all of the periodic trends that you're expected to know. So the IB expects you to know all of these trends here. And I wouldn't recommend just like rote learning them, because they usually always ask for explanations about why. But it's really easy to know the explanations for why. Usually it's got to do with electron shielding, or the distance from the nucleus. And so that all just falls under the umbrella of electrostatic attraction. So just always mind, like, what's the electrostatic attraction that's going on here? And if it's high, then it has certain properties. And if it's low, it has certain properties. But they'll always link back. The reasoning will always link back to electrostatic attraction for pretty much all of these trends that you have to know about. And so, yeah, atomic radius, ionic radius, ionization energy, affinity, and electronegativity. These are just some definitions. I remember this was in one of the term exams, term 2 or term 3, the definition of periodicity. And so it's just a fancy word to represent basically what the periodic table shows you. So as you go across every single period, as you go down every single group, there's a repeating trend that you can always see. Like before I said, as you go across every single period, that your metallic properties always decrease. That's an example of periodicity. So yeah, learn that definition because sometimes they'll ask it. Nuclear charge is the relative positive charge of the nucleus. So that's just the number of protons. So hydrogen has a nuclear charge of 1, helium has a nuclear charge of 2, etc. Effective nuclear charge is beneficial when you're talking about shielding. And so that's just the positive charge, not in the entire atom, but the positive charge that's felt by your valence electrons. So if I had like, I don't know, 2, 3, 4, 5, 6, 7, 8. I had like 3 out here. The nuclear charge, let's call this a geez, I don't know what I've just drawn. That is an aluminium. So if I call this an aluminium atom, then my nuclear charge is the number of protons in the center. And so that's equal to 13, because I said it was aluminium. But the effective nuclear charge is the charge that's felt by these valence electrons out here. And so you do that by taking the nuclear charge and subtracting the number of electrons, number of non-valence electrons. So basically all of the electrons, all of these electrons here. And the reason we do that is so that you can see how strong that electrostatic attraction is. It's like a little easier to reference electrostatic attraction when you use effective nuclear charge. And so here, my calculation for the effective nuclear charge would be 13 minus, and I've got 10. So my effective nuclear charge is positive 3. And yeah, that helps for comparisons between atoms. Like if you want to say one has a stronger force of attraction than the other, you usually refer to effective nuclear charge to explain that. And yeah, shielding, exactly what it sounds like. It's electrons, and electrons will always repel each other because they're the same charge. And so it's got to do with what effect do all these electrons, like these yellow electrons that I've highlighted, what effect do they have on the valence electrons and on the other electrons around them? So if you have more electrons that are packed inside of an atom, so your atom is like really big, so it has lots of electrons, then there's lots of shielding occurring. And so the electrons on the outside, like the valence electrons, will usually not feel very much attraction at all. And so it's easy to remove them. But yeah, that's just terminology, which you should probably already be familiar with. That's a relatively useless table, so I don't really care about it. Now let's go through all of the trends one by one. I'll zoom through these because it all goes back to the same principle. All right, so we'll start with atomic radius. Atomic radius, this is how it's defined, and you need to memorize that. The reason they define it as half the internuclear distance to the molecule of an element is because it's actually impossible for you just to get one atom and measure the size of it, because like, how do you know where the edge of it is? Like, what we've been learning all this time is that electrons can be found in all sorts of different places. So the only way that we can quantify the size of an atom is by bonding 2 of them together and then halving that distance. So that's like the best measure we can get, which is called the atomic radius. There are some elements that can't be bonded to themselves, like those noble gases, which I mentioned before. And so usually they either use an estimation or they just don't list an atomic radius at all. I don't know what the data booklet does, but they probably won't ask you for atomic radius if it's noble gases, so nothing to worry about. And as for the trends, if we're looking at down a group and across a period, down a group, it increases because there's more electron shells. So here, this diagram's a bit backwards. So this is at the top of a group, and remember, groups are the columns that go down. So lithium's up here, and potassium, if I recall, is directly underneath it. Actually, it can't be. It's sodium and potassium. So as you go down the group, atomic radius increases because you've got more shells. Pretty obvious. You can see that distance is more than that distance. And as you go across a period, it decreases because your nuclear charge is increasing, but there's no change in the shielding. So if I drew sodium, right, it'd look like this. And you can pretend all the inner ones are filled in. I can't be bothered to do those. But if I did chlorine, then it would look like this. 5, 6, 7. And so your effective nuclear charge here is, well, sodium has an atomic number of 11 and chlorine has an atomic number of 17. And so if I looked at my effective nuclear charge, so this is when you would quote your effective nuclear charge to support your point. Like if the question was explain how atomic radius varies across a period, then you'd use effective nuclear charge. And so you'd say my effective nuclear charge for sodium is whatever the nuclear charge is, which is the number of protons, which I said before was 11, minus the number of electrons in this shell, in the first and second shells. And so there's 2 in the first shell, and then there's 8 in the second shell. And hence it would be 11 minus 10, because it's 2 plus 8. And so your effective nuclear charge would be 1, whereas your effective nuclear charge for chlorine would be 17 minus 10, because your shielding hasn't really changed. That was what this thing is trying to say. There's no change in the shielding because I'm still subtracting by 10. Like there's only 10 electrons that are causing repulsion still, but my nuclear charge has increased and the number of electrons has increased. So there's more attraction overall, which is what your effective nuclear charge tells you. And since my effective nuclear charge is increasing, that means that the electrons in the chlorine atom are attracted to the nucleus more strongly than the sodium ones are. And so these sodium ones have less attraction towards the center than the chlorine ones do, and hence the sodium will be bigger than the chlorine, which is what this graph shows you. So this is atomic radius against chlorine, against period 3 elements, sorry. And yeah, see, the thing says what I said before. There's no atomic radius shown for argon because argon's a noble gas and it doesn't form covalent bonds. So we can't actually figure out how big it is. But yeah, that's atomic radius. Is that all good?
Yep.
All right, ionic radii, they work sort of similarly, but there's a bit of a jump in the middle of the pattern, especially when you're going across a period. And that depends on what sort of an ion is formed. So sometimes the atoms will form positive ions, sometimes they'll form negative ions, and that influences how big it's going to be. So that's simplified in this statement here, which you can rote-learn if you want. So the ionic radii of positive ions is always smaller than the atomic radii, and the ionic radii of negative ions is always greater, because when you have positive ions, what you're doing is, like if I draw lithium here, so it's got 3 protons in the nucleus, and then it's got 3 electrons. This is just a normal lithium atom. But when I make a lithium ion, it's going to want to get rid of this valence electron out here because it doesn't like having that valence electron there. And so once I remove that electron, now I've basically lost an entire shell. And so you can see that my atomic radius, my ionic radius has decreased. Like it's smaller than my atomic radius. And that's consistent with everything that forms a positive ion. And so all of your positive ions are typically going to be on the left-hand side of the table because it's easier for them to lose however many electrons than to gain a lot more. So for lithium, it's a lot easier to lose 1 electron it to gain 7. So it always forms positive ions. And as for negative ions, the opposite is true, because say I'm fluorine, and fluorine has a +7 charge. Yeah, okay. So fluorine's here, it's got a 7+ charge, and so it's got all of these full. 1, 2, 3, 4, 5, 6, 7. Oh heck, I can't count. So it's got 7. When it gains an additional electron, so I'll say it gains that 1 red electron there, now it's the nuclear charge that used to only be spread out among 7 electrons is now spread among 8. And so there's more repulsion amongst all of these electrons, but the same nuclear charge. So they're getting the same overall amount of positive attraction, but there's more negative electrons. And hence, since they're all repelling each other and there's not enough charge to go around, what happens is this atom, as it becomes an ion, will become ever so slightly larger. And so that's what you see on the graph here. Now, the trend is, therefore, across a period, like I said before, it's not like very clear cut, like it's not straight upwards or downwards trend. Instead, you've got all of your positive ions, they all have a smaller radius than they should have, and all of your negative ions have a larger radius than they should have. And so you get this like cut at silicon. Just know that about ionic radii, because I know there are especially some paper 1 questions that will always ask you like which of these trends is continuous across the period, and ionic radii isn't one of them. Yeah, that's not that important. Okay, this point is basically saying isoelectronic just means, this is a fancy word for same number of electrons. And so if you have isoelectronic ions, so they have the same number of electrons, but they're of different elements. So here you can see with sodium 1+ and magnesium 2+, they have the same number of electrons in their like overall. This one's got 10 and this one's got 10 as well. It's saying the size relative to each other will depend on the initial nuclear charge. So here, since sodium's nuclear charge is only 11, but magnesium's is 12, then, well, 12 is bigger than 11, so the attraction experienced by the electrons in the magnesium ion is going to be greater because there's more positive charge to be spread across the same amount of negative charge, and hence this one will be smaller than, magnesium will be smaller than sodium, which is what that statement says. And there's just another example, same deal, but just the opposite way around. So if you have negative charges, so these are both isoelectronic as well, but since phosphorus here has 15+ and sulfur has 16+, the sulfur has more of a positive nucleus, and hence it's going to attract those electrons more than the phosphorus is. Yeah, well, that's pretty straightforward. I don't think there's anything too confusing in that. All right, first ionization energy. This is a definition you will have to know. It comes back in topic 5, and I think we saw it in topic 2 as well. So it's just got to do with enthalpy changes, and it's removing, always remember, you're talking about 1 mole of something, so it's always 1 mole of electrons from 1 mole of atoms. So 1 electron from every single atom, but you've got 1 mole of those atoms is what's going on. And it's always under standard conditions, so it's this process here. So I've started off with some element, and I've taken away an electron from it, so I've made it a positively charged ion. Now, down a group and across a period. We already discussed this in 3.1, but might as well just go over it again with these fancy diagrams. So as you go down a group, your first ionization energy decreases because your atom is increasing. So remember what I said before, always link back to your electric attraction. So as you go down a group, you've got more electrons. So your atomic size or radius, use the proper terminology, atomic radius is always increasing. And if the distance is increasing,
Wait a sec, it's lagging.
Why'd you stop the recording? Oh, okay. The first ionization of energy of potassium is lower than the first ionization energy of lithium because it's easier to remove that valence electron now that it's further away, so it's got less electrostatic attraction and more shielding, and so that electron doesn't really feel like it belongs anymore, so it finds it easier to be removed. And there's just a diagram. This is just a graph. Sometimes I'll show you this to do with first ionization energies across group, not across, down group 1. So this is as you go downwards. So as your atom size increases, then your electrostatic attraction decreases because the valence electrons are further away. And if the electrostatic attraction is decreased, then the first ionization energy is also decreased because it takes less energy to remove that electron from the atom, is what you'd write down on your exam if they asked you something about this. As for across a period, it will increase because the nuclear charge is increasing, despite the fact that your number of electrons is also increasing. The shielding is staying relatively the same, and hence your effective nuclear charge is changing. So that's all explained in this paragraph here. So as you can see, this trend is vaguely increasing. There is a bit of, there's some strange anomalies here. And that's got to do with orbitals and other stuff. I'm not sure whether we actually have to know why that's there or not. I don't think so. But yeah, you just have to know the general trend. So you don't need to know about all these exceptions unless they expect you to. I don't think they expect you to know this. So it's all got to do with effective nuclear charge. And as you go across a period, then you're increasing your nuclear charge because there's more protons in every single atom, but your shielding staying the same because you're adding electrons into the same outer shell. And hence there's not much variation and it will typically increase. And yeah, there's a fancy diagram for you which shows how the shielding is not changing. So all these blue electrons, that's the shielding that's going on. But what's happening on the outside is you've got more electrons in argon and you've got a higher charge as well. And so these guys will be attracted much more strongly than these guys will be. And so sodium is larger than argon, substantially larger. And therefore, the first ionization energy for argon is greater because the force of electrostatic attraction is greater. So always remember, if the electrostatic attraction is high, then that directly corresponds to a higher, where the hell is my eraser? That directly corresponds to a higher first ionization energy as well. Okay, is that all good?
Yeah.
All right, next. Electron affinity. And this seems to only talk about first electron affinity, so I might want to change that title. This is another definition you should know from topic 5. Again, always talk about moles of things. So it's 1 mole of electrons, not being removed this time they're being added to 1 mole of gaseous atoms. And so I'm making all of my gaseous atoms negative ions, is what this equation shows. The first electron affinity for almost all elements is exothermic, because I don't know how you can understand this from, you don't do physics, do you? So this is going to be a bit, the intuition behind why this is the case is a bit difficult to explain. I could explain it, but it might get a bit confusing. Basically, this is a diagram that you might see sometimes to do with the energy of an electron depending on how far it is from the nucleus, and it looks a little something like this. So this is saying when an electron, so this is like the distance, my x-axis is the distance from the nucleus, and my y-axis is the energy. Now, electrons will always aim for the lowest energy level as possible because that's the most stable. That's like what it means. If something's low in energy, that means it's more stable. And so what's going on in this first section is this is basically when an electron is forced too closely into the center of an atom. Not that bottom section. Oops, I went a bit too far. This bit. This bit here is like if I'm forcing that electron so close that it wants to get away. It wants to move further away. So it doesn't like existing in this region. It also doesn't like existing in this region because although it can exist quite far away from the nucleus, that's not a very stable position for it to be in because it's still got a higher energy than its potential lowest energy, which is at this point here. In fact, when it's around this section, that's like when we're talking about, you know how in topic 2, you have like your electrons jumping up another level and then dropping back down again. That's like when they're this distance away from the nucleus. And when you drop down in energy, effectively what it's doing is it's going back. So it's moving further closer to the nucleus. So its distance is decreasing because it wants to get back to this sweet spot here. So this is where every electron wants to be. So let's say when you add one electron into pretty much any atom, that's a favorable thing for it to do because this line here, this line, I could draw it, I could extend that to infinity. That's a bit like asymptotic, asymptotic, what the hell, asymptomatic? It's asymptotic. And hence, if I'm bringing an electron all the way from infinity, so it's like an electron all the way out here, it would rather be in this divot here because it always wants to be where there's the lowest energy. It would rather be in this divot than it would want to be all the way out here, which is why we say the electron affinity is usually exothermic. So it's usually a pretty low number because as that electron joins the atom, it releases energy because it's gotten closer, right? Because remember the definition of electron affinity. So that's my enthalpy change when I've added electrons to an atom. So when I add this electron, let's say I've got some electron floating around and it comes into my atom and it falls into this divot. See how my energy change, if I refer to my y-axis, this is the initial energy of the electron, and that's the final energy because it's gone into that divot. And since it's done this process, then it's effectively lost energy, and hence we call it an exothermic reaction. It's an exothermic process because I'm releasing energy as I go from a higher energy to a lower energy. So that's what electron affinity is all about. I can't recall them ever actually asking the reason behind why first electron affinity is usually, what the hell has happened here? I don't recall like when they've ever asked to explain it like that in an exam. So if you can't be bothered with the explanation, just remember this statement. They're almost always exothermic. And what exothermic means is that the electron affinity is represented on a scale like this. So it's the more exothermic you are, the further down the scale you are, because this has got to do with how much energy has been released. Remember, exothermic's always negative. So the more negative you are, then the more energy that you've released, and hence they say your electron affinity is higher. So here, this says that as you go down a group, specifically group 17, your electron affinity decreases. Now, what it means by decreasing is the magnitude of that number decreases, because actually you can see that the trend here is going upwards. What it means is actually refer to the value there. So here it's 360, and then there it's 290. So it's telling you to ignore the negative sign. And hence, as you go down that group, your electron affinity is decreasing, like decreasing. It's not actually decreasing, the numbers are decreasing. So you're letting out less energy every single time, like for all of these atoms here, as you go further down the group, you're releasing less and less energy. And so the reason for that is because your atom is getting larger. And so remember I said always link back to electrostatic attraction. If my atom is larger, my electrons on the outside, they don't feel as attracted to the inside as they would be. And so if I wanted to add yet another electron to join, even though my atom's already really big and I've got several layers, then it's going to be, that electron's not going to be so keen to join, essentially, because there's already a heap of electrons there. The shielding's already big, the repulsion's already pretty high, and hence the energy drop as that electron moves from outside the atom to inside the atom isn't as great. So that explains what's going on in this first graph here. And this is to do with the crosser period. So I'm in the same period, so I've got the same amount of shielding, but I'm trying to add another electron to my outermost shell. And what it's saying is generally your electron affinity increases. Now I know the graph is going downwards, but from what I said before, so just look at the magnitude of the numbers. So ignore the minus signs. So aluminium's got an electron affinity of 50, whereas chlorine has got one of around 400, and so it's increasing. And the reason for that is because what we talked about before, as you move closer to the right-hand side of the periodic table, those atoms want to gain electrons more because they want to become stable, right? So the atomic radius is decreasing, your effective nuclear charge is increasing, which is what this sentence here says. So as you add more electrons, it wants to get another electron to make itself more stable because it likes having more electrons. It's trying to achieve a full octet like they usually talk about. Now, I don't think we need to know about this. Silicon and phosphorus anomaly. Yeah, all right, I'll explain this. So silicon and phosphorus have this little jitter, which apparently, if I've got it in my notes, then you have to probably know why. Phosphorus and silicon, if we refer back to our periodic table here, they're these guys here. And so they're both P block, right? Remember, this is my P block on the right-hand side here. And so if I did my electron configuration for silicon and for phosphorus, it would look like silicon would be 1s2, 2s2, 2p6, 3s2, 3p2, right? Because I've gone 1s2, I'll do this in a different color. 1s2 is these two, and then 2s2, 2p6, 3s2, 3p2. So I've gotten to silicon now. Whereas phosphorus has one more electron. So phosphorus would be 1s2, 2s2, 2p6, 3s2, 3p3. Now, if I drew out the electron configurations for this, and I'm going to skip these guys because they're not relevant. So if I just did 3s and 3p, then it would be 3s2, 3p2. So that's silicon there. This is silicon. And then phosphorus would look like so. Now, when we're considering electron affinity, we always want to think about what would happen if I wanted to add one more electron. And if I added one more electron to silicon, that would be relatively easy. Like it would release more energy. This would be more exothermic. And the reason for that is because there's not really that as much repulsion that this additional electron would face, because it would fit in its own orbital like that. And typically when the electrons are in their own orbitals, there's much less repulsion. But if I wanted to add an electron to phosphorus, it would have to join an orbital that's already got something in it. It can't have its own orbital for itself, and hence there's more repulsion. And so the energy divot that I was talking about isn't as low as it is for silicon, and so it's a little less exothermic than silicons would be. That doesn't mean that it isn't exothermic, it's just less exothermic. And so if we look back at our graph here, you can see there, phosphorus has a value of around 75 and silicon has a value of around 130. So it's less exothermic than silicon is. So that's just explaining that little variation in the trend there. Does that all make sense?
Yep. So wait, so if it's like, if the number for the electron affinity is larger, it means it's easier for it to like gain another electron?
Yes, exactly.
Okay, yeah.
Yep. All right. Now, last is electronegativity. Oh, yay. Okay. This is a definition they will almost definitely ask you. It's a stupid definition. Once I got marked down for it, and Dr. Colley almost felt sorry for me because I got it wrong because I forgot like one word. But the IB are very, very picky. And so you just have to memorize that word for word. It's the measure of the ability of an atom in a covalent bond to attract a covalently shared pair of electrons towards itself. So it's basically talking about, if I look at this scenario here, it's measuring the ability for this fluorine atom, since it's in a covalent bond with hydrogen, it's measuring its ability to attract these electrons to itself. If I was talking about the electronegativity of fluorine, and if I was talking about the electronegativity of hydrogen, that's its ability as an atom to attract a covalently shared pair of electrons, which is these two electrons here, towards itself. And so it would be that force there. Now, electronegativity doesn't have, it's not like an actual quantifiable, like it's not a physical quantity. So when someone talks about the electronegativity of something, it doesn't have like an actual meaning. Like it's not something you express in joules or something, where like with energy, it's something you actually properly quantify, like it has meaning. Electronegativity is a relative scale. And so this dude who made the periodic table, I think his name, he wanted to add to the periodic table a measure of how well certain atoms can attract covalently bonded electrons to themselves. And so if I get up my periodic table, actually, there was a guy by the name of Linus Pauling, I think it's him, because it's called the Pauling scale. It's the most commonly used electronegativity scale. And if I can get my data booklet up, whenever it wants to pop up, he basically decided fluorine is going to be the most electronegative element on my periodic table. Oh, here it is. He says fluorine is going to be the most electronegative, and I'm going to assign fluorine a value of 4, which is what this says. So here in my little thing here, it says electronegativity is the number at the bottom. Fluorine's got an electronegativity of 4. And he says, I'm going to call this 4. 4 is going to be the highest number in my scale, because I'm making my scale, I can do what I want. And I'm going to relate the electronegativities of every other element relative to fluorine. Now you'll see actually that helium and neon, pretty much all of your noble gases don't have an electronegativity value, and that's because they don't really get covalent bonds. Like I said before, xenon occasionally can, which is why it has a number, but these guys pretty much never get into covalent bonds with other things because they don't need to. They don't want to share their electrons with anybody else. They don't need electrons from anybody else. They're just independent. So they don't have values, but pretty much all of the other ones do. So it's a relative scale as to how strong the attraction is for an atom to attract an electron pair towards itself. And so if we look back at the diagram here, this is considering trends. So as you go down a group, your electronegativity decreases. And so that means your ability to attract that electron pair is less than than the other atom that's in that bond. And the reason for that is because your atomic radius is increasing. So again, remember, always link back to electrostatic attraction. So if my atomic radius is increasing, then the electrons in that valence, those valence electrons in your outermost shell, they're going to experience the lowest, like the least electrostatic attraction. And hence, since there's less electrostatic attraction, it can't bring these shared electrons close towards itself. So here, then chlorine would have, since it's further away, it would have a lower electronegativity than fluorine. Okay, and next, across a period, my electronegativity increases. And again, always link back to electrostatic attraction. And so that's to do with effective nuclear charge, like we mentioned before. So the shielding is staying the same because I'm in the same period, but my nuclear charge is increased, like between nitrogen and fluorine. Nitrogen is to the left of fluorine. And so nitrogen's electronegativity is lower because nitrogen has a 7+ charge, fluorine has a 9+ charge. And so these electrons on the outside of fluorine have experienced a stronger attraction than these ones in nitrogen. And so that means that its ability to attract this shared pair is greater than nitrogen's ability to attract that pair. And so, I mean, this wouldn't be a problem for paper 2 if they asked you, because you could literally just refer to your data booklet and see how the numbers change. So what you typically would say is that electronegativity increases that way in a periodic table. So bottom left, has the lowest, top right has the highest. And electronegativity is also sometimes used to explain bonding. So they'd say, if the difference in your electronegativity values is greater than 1.8, so greater than 1.8, they call that ionic. Now that number is really arbitrary, but it's basically saying the larger the difference, then you would call it ionic, and if it's less than about 1, I think, then you call it covalent, which is why when there's bonds between like this block of elements, they're usually covalent bonds, whereas if I bond something from this side of the periodic table to this side of the periodic table, that typically results in an ionic bond. So electronegativity values have a lot of usefulness, but don't accidentally use them for the wrong purpose. Because I know people sometimes just think that electronegativity is just how strong the attraction is between your outermost electrons and your nucleus, and that's not the case. It's always covalently bonded electrons, and so it gives you a slightly different meaning than it otherwise would be. So use it with caution. But yeah, that's all about electronegativity. I think I need to explain. Is that all good?
Yeah, that's good.
All right. Okay, now these are the properties of elements in group 1 and 17, because they're very important in terms of bonding and in terms of the fact that their characteristics are pretty like definite. So these are just some general things you have to remember. They're all got to do with the structure and the bonding of all the group 1 elements. So like I said before, they're all alkali metals. And that means, one, that they're all metals, and metals do all of these things here. But two, that when they react with water, they form alkaline or basic solutions. And okay, that's down there. So these are just properties that you have to remember. They apply to pretty much all metals. Highly reactive, because the reactivity of an atom has got to do with how easily it can lose its outermost electrons. So if you can lose them more easily, then you're more reactive. And metals can do that because, like I said before, they have really low ionization energies, so they just let their electrons go willy-nilly. So it's got high reactivity. It's soft, and like soft, you wouldn't think of it to be soft. Like you don't intuitively think metals are soft, but there's like videos on YouTube and stuff where people are touching sodium and it sort of just bends. It's like very malleable. And the reason for that is the electrons in this C that you have in a metallic structure, they basically serve as a lubricant between all of your positive ions. And so if you just imagine you have a bunch of positive ions, so these are all of my positive ions that have donated 1 or 2 electrons into this C, and these are all my little electrons. Then you can imagine that if these electrons are delocalized, we call them the delocalized because they don't have a specific position where they have to be, then they can serve as like a sort of in-between layer for all of these other positive charges to sort of float about. And hence it makes it quite soft. So it's quite malleable, which is why metals are also ductile, because you can turn them into wires, you can shape them into things. That's because of that sea of delocalized electrons property that it has. And the other thing is metallic bonding, because obviously a metal is going to bond. So the way that structures hold themselves together is from the electrostatic attraction between my positive ion and my negative electron. So all of these little attractions that are going on, and like they change. So this is saying that the melting point, that's what that stands for, melting point decreases as you go down the group as the ions get larger. Because again, remember, always link back to electrostatic attraction, which is what this diagram is. The further down that group that you are, so lithium is all the way up the top and rubidium is like second last. The further down you get, the further away your valence electrons are, and hence the less electrostatic attraction there is. And if there's less attraction, that it's easier for you to separate these atoms from each other, right? Because they're all competing for, say, this one electron, but they're really far apart. And so the attraction is not that strong. So it's easier to break these bonds than it is to break these bonds because they're a lot closer to your, so your attraction is strong. And so that just explains why this is going downwards. Right. Now, these are two reactions that you have to remember to do with the group 1 elements. We rehash all of this in topic 8 when you go through acids and bases and things. Here, this is just saying if I have a group 1, this is the group 1 metal that I've got, and I react it with oxygen, I get something of this form. So for example, if I had sodium and I reacted it in excess gaseous oxygen, I would get, I need 2 of these, whoops, I need 2 of those. I would get sodium oxide is what that's called. So that's one of the processes you have to remember. And this is what they mean when they talk about basic substances. Because if I dissolve that in water, I would get an alkaline solution, right? So if I put this into water, do I want to do this reaction right now? If I stick this into water, then my sodium is going to react with these oxygen and hydrogen thingies, and I'd get NaOH plus what's left over. I think I need 2 of these. I need 2 of those. Oh wait, no, that's already my equation done. What am I talking about? This is what you get. And remember, if say I had this, and that's obviously a liquid, this is aqueous. If I put sodium hydroxide into water, I put it into water, then it splits up into these constituent ions. And anything that releases OH is a base. And so sodium hydroxide is a base, which is why we call sodium an alkali metal, because when it's in its oxide form and it reacts with water, it will give me a basic substance. So that's where we get that name alkali metal from. And so you don't have to remember that reaction, just remember this one. But that reaction comes from topic 8, so you should know it as well. And this is a reaction with water. These are like those exciting YouTube videos that you can watch online, where basically people just get a big chunk of like cesium or something, rubidium, and they just chuck it in a big tank of water and it just blows up. Like, it's such a vigorous reaction because remember, those alkaline metals are really reactive. And so when they get put in something, they just want to react a lot more. And as you go down the group, your reactivity increases because your valence electrons are moving, they're further and further away from your nucleus. And so the atom wants to get rid of them more than they would if it was something like lithium, because it's further away. They just don't want to have to deal with that outside electron. And so it becomes a more vigorous reaction. And this is the equation for that reaction with water. So if I had sodium, for instance, and I chucked it in with water, M is just a standard word for like substance. It doesn't actually mean, it doesn't actually represent any element. Then we have, again, the formation of sodium hydroxide, which makes it alkaline, and the production of hydrogen gas, which is what makes that whole entire explosion thing, because you've got gas in water. The gas wants to escape, essentially, and so it'll blow up. But yeah, that's group 1. Is that all good?
Yep, that's good.
All right.
So we have to remember those 2 equations, right? Like the general equations. Okay.
Yep. And then group 17, the halogens, pretty much the opposite of what I said before. So they're non-metals, because remember they're on the right-hand side of the table. They don't like metallic bonding. They prefer to be covalently bonded. I think all of them are covalently bonded. And so they like to covalently bond with themselves, which is what makes them diatomic molecules. And so that means there's two of them that are chemically bonded together. So you'll never ever find chlorine, like gaseous chlorine, just existing on its own like this. You'll always see Cl2. Like there's basically no instance where you'd see it on its own unless it was bonded to something else. And that goes for pretty much all of them. So fluorine would be like that, bromine would be like that, iodine would be like that. They all like to exist in pairs. And melting point and boiling point is also very low because what I said just then, they only covalently bond. And so the covalent bonds are between individual molecules. So like, say these are just a bunch of chlorines. But that means that they're non-polar. So they've got no real polarity going on. And so the forces between the molecules, so the covalent bonding is within the molecule. So that's like this attraction within them. But the intermolecular bonding that's between different molecules, that's only London dispersion forces. And remember, London dispersion forces are really weak. So they're like the least strong out of all of them. And so this is actually quite low, and hence their melting points are low and their boiling points are low because they have to rely on London dispersion forces to do everything. They've got no polarity of their own. They're not some sort of giant covalent structure. They're just floating around. They look like this. So yeah. As for trends across down the group, as you get bigger, you have more electrons, essentially. And hence, if you have more electrons, your London dispersion forces increase. Because London dispersion forces have everything to do with instantaneous dipole-dipole interactions. So basically, if I have like a cloud of, let's call this chlorine, and there's another chlorine here, there's just a bunch of negative electrons that are floating around within this sphere of chlorine. I don't even know if I did the right number. If I didn't, it doesn't matter. So there's just a bunch of them floating around. And so London dispersion forces are when occasionally there will be, just because these have been moving around, occasionally there'll be more on one side than on the other. And so if that happens in one molecule, like is this on this side, I'm not referring to the top anymore. So I've got lots of them on the right-hand side. What that will do is that will induce a dipole in the other side as well. So that will repel the electrons in this second chlorine. So they'll want to go onto the right-hand side as well. And so what happens is you have a partially negative charge here. That's the sign we use for partial negative. And since all your negative charge is on this side, that means that this side is partially negative, and hence this side is partially positive. And what happens when positive and negative are close to each other? They attract. So this attracts to that, and hence that's London dispersion forces. Now, if all of these electrons decided actually, hey, we're going to move to the other side now, then that dispersion force is broken. Then it'll form some other bond with another chlorine atom that happens to be on this side, which is why it's really temperamental. It's not very strong, but that's what London dispersion forces are. Now, if I increase the number of electrons, and so I have a greater number of electrons that all happen to be on the same side, so this isn't chlorine anymore, this is something like bromine or something. If I have a heap of them, then I can induce an even greater dipole in the other one as well. And so this partial negative charge is increased, and so the partial positive charge is increased, and so my attraction is even greater. And so this is saying, essentially, the more electrons an atom has at its disposal, the higher the London dispersion forces, which is what this graph is showing. And so if your London dispersion force is greater, that means that your attractive force is greater, so they're staying closer together, all of your molecules, and hence it's harder to break them apart, which is why your melting point increases. Because iodine has just a ton of electrons. Fluorine doesn't have that many. So iodine can have a really high London dispersion force, and in doing so, then they're really closely attracted. All the molecules are closely attracted to each other, so it requires more energy for them to be broken apart, and hence your melting point is greater. So that explains the trend we have in this graph. Now, these are two reactions that you have to know. This one's not as important, but this one is. So we'll go through them separately. So reactivity, before I said reactivity for the group 1 elements increases, and group 17 is pretty much the opposite in every single regard, and so their reactivity decreases. So if you think about it, again, reactivity has got to do with valence electrons and how much those valence electrons want to participate in reactions with other things. So if I have something like chlorine, which only has one shell, and then I have something like bromine, which I don't even know how many shells it has, but it has a lot. Let's give it like 3. Actually, I should just check. I'm being a bit lazy. Yeah, it does have 3, but chlorine has 2, so I'm being dumb. As there's more shells, there's going to be like 7 electrons out here, right? 1, 2, 3, 4, 5, 6, 7. Same with chlorine. There's 7 on the outer shell. But chlorine wants to gain an additional electron far more than bromine does. Because remember, electrostatic attraction. So the further away I am from the bromine, the less, like the further away any electron is from the center of the atom, the less that atom really cares about it, so to speak. And so bromine's just a bit lazy. It doesn't really want to get into reactions as much as chlorine does anymore, because these electrons on the outside, they're very highly shielded. They don't feel very much of an attraction to the nucleus. They're not really, like, they don't really want to engage in reactions anymore because it's less worthwhile for bromine to get another electron than it is for chlorine to get another electron. And hence your reactivity decreases will generally decrease down the group. This is just a general reaction that you should remember, which is between alkali metals and halogens. So this, pretty much the most common version of this that you'll ever see will be in the formation of table salt. So that says 2m plus x2 will turn into 2mx. Much. Oh, look at that. Now, the most common version of this, where m is the group 1 element and x is your group 17, the most common version you will have seen would have been with sodium and chlorine to produce table salt. So that's one that I usually remember. I find it easier to remember like a specific case than a general case, because more often than not, they'll ask you for a specific case. And it also, like, you get used to seeing certain equations over time, and this is just one that's just stuck in my memory. So yeah, I recommend just remember this one and you'll be all good. Displacement reactions don't really belong here. They're not really that important at this stage. We'll go through all of them when we do redox reactions this year, so I don't feel the need to go through that right now. But essentially what it's saying is, because your reactivity decreases down a group, so remember chlorine, bromine, and iodine are like this. So the reactivity is decreasing. So it gets less reactive down the group. So it's saying if I had chlorine and bromine ions together in solution, so I have chlorine, but it's bonded to itself, and bromine, but it's in ionic form, what it's basically saying is chlorine wants to get to a state where it's also got a negative charge. Because remember what negative charges mean. A negative charge on a group 17 means it's got a full outer shell. And so what it's saying is if I react these two things together while they're in solution, say, since the chlorine is more reactive than the bromine, so this chlorine wants to get a full outer shell more than bromine does, essentially, what can happen is the 2 extra electrons that bromine has, because remember bromine usually has 7 valence electrons, but now it's got 1 additional one, and there's 2 of them, so there's 2 additional electrons. What chlorine can do is it can displace those additional valence electrons. And so what happens is chlorine gains those electrons, and then it forces bromine to bond with itself because chlorine is more reactive. So that's all got to do with the higher up in the group you are, the more reactive you are, and hence you can essentially take electrons from other atoms. And so that's called a displacement reaction. So that's written here. This isn't very important to do with topic 3, but you'll see it in redox, so I'll talk through it. And this diagram here is an experimental thing. So if you want to see how like that displacement reaction occurring, you can mix two of these solutions together and then you just see how the color of it changes over time is what that diagram is there for. But that's not very important. If you don't get it, it's not the end of the world. We'll go through it all this year anyway. Essentially, the more reactive you are, the more you want to steal other people's electrons if you're group 17, and hence, since chlorine's more reactive than bromine, it's taken those two electrons. So it's gotten a full outer shell now, and bromine's been forced to have an incomplete outer shell. But yeah, that's group 17 done. Any questions?
Nope.
All right. Oxides, heck, yeah, I hate these two. This is all topic 8 stuff. It's topic 8 stuff that gets addressed earlier because it's got to do with what certain elements do when they're reacting. I suppose I can just run you through these. There's nothing more that you can do than just memorize. It's literally like there will be questions in paper 2, which are just 2 markers that say, write down the reaction between sodium oxide and water, and you'll just have to be able to do that. It would be like, if you can't really be bothered, just memorize it, is my advice. But yeah, this is saying a basic oxide is an oxide that when it reacts, it forms an alkaline solution in water. So just memorize these 2 equations. Is my advice on that. So this is if you have 1+ charge, because remember sodium has a 1+ charge, then you need 2 of it because oxygen has a 2- charge. So that's why there's a 2 there. But since magnesium has a 2+ charge, oxygen has a 2- charge, there's no subscript. And the products are slightly different, but you can see both of them form OH, and hence they both form basic solutions, which is why we call these metals alkaline metals. So this is an alkali metal, that's an alkaline earth metal. Amphoteric oxides react with both acids and bases. Memorize this guy. The reason that it's amphoteric is because if I refer back to my periodic table, aluminium's sort of occupied this sweet spot here, where it's got like, it's close to both sides, and hence it can react with both acids and bases, and that's why it's sort of important. These you don't have to remember, just remember that aluminium exhibits properties of being both a metal and a non-metal oxide, and that's why it's amphoteric. And acidic is something that reacts with water. As an oxide, it reacts with water to form an acidic solution. So the way I think of it is, since I said metals form basic solutions, it's typically the non-metals that will form acidic oxides. So see here, there's phosphorus and there's sulfur. They're both non-metals, and when they react with oxygen, then they make this compound, and then when they react with water, you get an acidic solution. So you call it an acidic oxide. So again, just memorize those equations. There's nothing more you can do. Pretty useless table. I don't know if you like that table. I don't like that table, but it just goes through everything that we talked about before. And nitrogen oxides, not important. You would have gone through them in topic 8 anyway. I mean, if you want to read that, you can, but it's, yeah. If they ask you a nitrogen question, honestly, I just skip it in the exam. It's the IB trying to be all environmentally friendly and stuff, because they like to be, you know, they always talk about how they're global minded people, and so nitrogen oxides have got to do with acid rain and all of that, which is why they focus on it a lot. It's not actually that important. So yeah, read that if you want, but essentially this is, yeah, it's just a bunch of things you have to memorize, and then that. So is that all good? Yeah,
that's all good.
All right. Do you want to continue on to 13?
Sure, yeah, let's go.
All right, let's go. So 13's got to do with D-block elements. Now, D-block elements and transition elements, they're different terms which refer to the similar thing, but not the same thing. So when I say D-block elements, that's everything that has an electron in the D subshell. But transition elements are a certain section of the D block. So this is the first row of the D block, which is all of these elements here. Transition elements, oh, look at this, I wrote it right here. They're different from D block elements because they're elements that can form one stable ion with a partially filled D subshell. Fancy terminology for basically, if we're looking at the first row, zinc gets cut out because zinc can't form a stable ion with a partially filled D subshell. In fact, when it does form an ion, see its electron configuration here. When it forms an ion, it loses those two 4s electrons, but it doesn't lose any of the D electrons. And remember, the D block, the D subshell, like in your electron configurations, has 5 orbitals. And so if I have 10 electrons in total, I filled up everything. So zinc is not a transition element, but scandium is. Now, I got that wrong in an exam once, and I'm still salty about it. But the IB, it's like a bit disputed whether scandium is or isn't, but the IB treats it as a transition element because when it forms a compound that has 2+ charge, so it's lost these 2 electrons, it still has a partially filled D subshell here with this 3D1. So there's 1 electron in that subshell, and hence it's still counted as a transition element. So the main thing I want you to remember here is the definition of a transition element. So 1 stable ion, partially filled D subshell counts as a transition element. Now, the IB doesn't care about transition elements and D block elements beyond the first row. So these guys are the ones that you'll have to get pretty familiar with. And it's just a bunch of trans and stuff. All right, so what does this say? Okay. This is basically, these diagrams, don't get too scared about what they're trying to say. Essentially what it's showing you is that the trends that I talked about, those periodic trends that I talked about, are emphasized more so in other periods than with the transition metals. And the reason for that is because transition metals are very, very similar to each other. So they vary in the number of electrons and they vary in their nuclear charge. But other than that, their chemical properties are pretty much, they're very consistent. Because when you're a metal, remember you're donating all of those electrons into this sea of delocalized electrons. And hence, if you donate like 2 electrons, if each of these donates 2 electrons, then they pretty much all look like the same thing. And that's why here, it's saying in period 3, I've got this pretty obvious trend where my first ionization energy increases. But for transition elements, the trend is relatively constant because, like I said before, they're not very distinguishable from each other, and hence you get this pretty straight line as you go across the period. Same with atomic radius, they're pretty consistently shaped. So that's just things to note. Transition metals, very similar to each other. Now these are properties in the chemistry syllabus guide. They literally just list all of these and they expect you to know that all of them are what the properties of transition elements are. So yeah, memorize those. This is relatively self-explanatory. They're metals, so they're going to exhibit properties of metals. They can form more than 1 oxidation number, so that means they can, in that sea of delocalized electrons, they can donate 1 electron or 2 electrons or 3 electrons. It depends on which element you're talking about, but typically they can do more than 1 oxidation number. So oxidation number here basically just refers to how many electrons it's donating. Forming complex ions and colored complexes, that's to do with having them with ligands and stuff, so we'll get to that later. And magnetic properties has got to do with how their electrons are arranged. So that's all we're going to go through all of those things in the next couple of pages. These are just electron configurations of them and their ions. Remember, copper and chromium, we talked about in topic 2, they have slightly different electron configurations to everybody else because they have that partially filled s subshell because they want to fill all of their d orbitals. So remember what that looks like. That basically means since it wants to have 5 of these, we'll only put 1 in there. That's for chromium. But yeah. Always remember that the 4s electrons are lost first, which is why also pretty much all of your transition metals can form 2+ ions, is because they always lose their 4s electrons first, and there's typically always 2 of them. Chromium and copper have the advantage of being able to lose only 1 because they only have 1 4s electron. But yeah, let's go through. We're going to go through that in here. This is a table that's available in your data booklet, so don't fret. I've never seen a question that needs it. It just shows that there's variable oxidation states for every single transition metal, and see, copper has the advantage of being able to do this. The reason for this is because 3D and 4s are very close to each other, and like they say that 4s is ever so slightly lower than 3D once you've filled up the shells, but they're really close. Like if this was my energy axis, they would be that close to each other. And hence, for your transition metals, what you're doing is you've already filled 4s, and so you're just adding electrons into here one by one. And since they're so close in energy, removing electrons from 4s and 3D, it's not significantly different. Like remember before when I was talking about removing electrons from like a magnesium atom or something, it gets much, much harder as you remove each one because you're breaking into new shells. Here, since they're all pretty much of the same energy, removing one isn't more difficult than the other, and hence it can lose or keep as many electrons as it wishes, depending on what sort of bond it's in. And so this tells you how many electrons it can lose. So manganese can lose up to 7, depending on what it's bonded to. That's an oxidation number. Copper can lose as few as 1. Yeah, manganese is like in the middle of the table, which is why it's got that many oxidation states available to it. Yep. Magnetic properties have to do with, again, the number of electrons that transition metals have. So there are 3 different types of magnetism: ferromagnetism, paramagnetism, and diamagnetism. And I've listed them in that order because as you go down, this is less strong. So ferromagnetism is the strongest sort of magnetism. It's the kind of magnetism you think of when you're talking about like fridge magnets and stuff. And it's got to do with permanent magnetic fields. So ferromagnetism is only exerted by these 3 elements. Remember those. And the way that it happens is in all of those elements, you have such a large number of unpaired electrons that if you put them in a magnetic field, all of those electrons line up with one another and they make their own magnetic field. And so they become magnetic. So if I look at iron, for instance, which is where the name ferromagnetism comes from. Ferrum is the Latin word for iron. If I open up my periodic table and I find where it is, so it's there. So if I want to write my electron configuration for that, that would be, if it does that down the bottom here, oh, it does. Oh, splendid. Okay, so if I look, what the hell? So if I look at iron, but I don't want to think of it as 2+, because that's got to do with the next thing that I'm talking about. So this is iron in its normal state. So it's got 26 electrons, and it's got, in the 4s and the 3D, it's got 2 4s, and it's got 6 3D. Now, the reason it can have ferromagnetism is because it's got all of these unpaired electrons. And unpaired electrons are useful because if I put this into a magnetic field, I can line those electrons up to make magnetic fields of their own. Now, it's a bit difficult to explain, but just that's how it happens. So the more unpaired electrons you have, the stronger the magnetic field is that you can form, which is why these 3 elements can form ferromagnetism. Now, paramagnetism is different. It's also caused by unpaired electrons, so it's similar to ferromagnetism. So everything that does ferromagnetism does paramagnetism, and also does diamagnetism as well. But paramagnetism is exerted by pretty much every single transition element that's got at least 1 unpaired electron. So if we look at something like chromium here, 3 unpaired electrons, and hence it can be paramagnetic, because what it is it's induced magnetic fields. So just think of it like you don't ever need to write down what the definition of these are, but just think of paramagnetism as always to do with unpaired electrons. Diamagnetism is in the case where you have paired electrons. So it's exerted by every single metal. Every metal has diamagnetism. But it's not very strong because it's just a magnetic field that's in the opposite direction to whatever field it's been put in. And so if I had an element that had all paired electrons like this, it wouldn't have, it's not iron, it wouldn't have ferromagnetism because there's no unpaired electrons. It wouldn't have paramagnetism, there's no unpaired electrons, so all it has is diamagnetism. So I wouldn't get too fussed with the definitions of all of these, just remember when they occur. So diamagnetism, whenever there's paired electrons, paramagnetism, whenever there's unpaired electrons, and ferromagnetism, always these three elements. That's the simplified version of this page here.
Yep.
Here's an example of something that's only diamagnetic. So that's copper 1, because look, everything is paired. There's no way for it to make a magnetic field of its own. So yep, is that all good?
Mm-hmm.
All right, complex ions. This is what we were talking about with ligands and things before. So a complex ion is a central metal ion that's surrounded by ligands. This typically occurs in water. So this is an example of if I put iron 2+ in water, the water ends up acting like a ligand. Now, if you remember back from topic 8, ligands are Lewis bases. Because remember what a Lewis base is. A Lewis base is an electron pair donor, right? Lewis base. This is a topic 8 link. We'll probably see it again once we get to topic 8. So since Lewis bases are electron pair donors, that makes ligands Lewis bases. Because see in this example here, the oxygen is donating this electron pair to, effectively it's donating this electron pair to iron. And hence the central metal ion, you could also call a Lewis acid because it's accepting, because it's an electron pair acceptor. Now, the definition of a ligand is any sort of negative ion or molecule that has at least one lone pair of electrons. And those lone pairs of electrons can be used to bond to a metal ion, which is exactly what's going on in this case here. And the name of the bond that's occurring is a dative bond or a coordinate bond or a coordinate covalent bond. You can call it whichever one of those you want to. And so dative bonds aren't exclusively applied to bonds between ligands and central metal ions. They refer to any bond where both of the electrons come from the same species. So by species, it just means atom or like element or something. So one of the examples of that is, can I come up with an example? Yeah, I can't be bothered to come up with an example right now, but I'm sure I could. As in, this is an example of a coordinate covalent bond, but as in like in a normal molecule, they can also be formed. So this is not exclusively applied to this relationship. It can also be applied to actual like covalently bonded molecules. There are other ways of representing what is shown up here. The way that you write it is like this. So you write first whatever metal ion you're bonding to, you write the ligand, and then you write how many of them there are. And if it has a charge, if your thing has an overall charge, you always have to put it in square brackets and then put the charge on the top. You also have to put it in square brackets when you're representing it diagrammatically, like in these diagrams here. You still need to put the brackets around it and write 2+, or else people don't know where that 2+ charge is coming from. Now, every transition metal, except for titanium, forms an octahedral complex ion. That's not that important. It's basically saying every single transition metal forms complex ions of some sort, though, because you can form complex ions of different shapes. So here, there's one that's tetrahedral, one that's square planar. A few of these will stick in your head after a time, like this one definitely has stuck. They can undergo substitution reactions, not important. If you want to read that, but yeah, it's saying you can change the ligand sometimes. So if you have copper bonded with water, but there's also chlorine available, it forms an equilibrium where some of this copper will actually form a coordinate bond to the chlorine, and this is an equilibrium, so both of these things exist in the solution. But yeah, that's not that important there. It's just saying that the transition metal can bond to several different ligands if it wants to. Yeah, and the way of figuring out the oxidation, like the way of figuring out the charge on this thing, is you'd have to first know the oxidation state of your central metal ion and then the charges of your ligands. So in this scenario, I would be able to figure out the oxidation number of iron because I know that water is neutral. So this has a zero charge. This has a zero charge. But this number here tells me that it's overall got a 2+ charge. And so that 2+ charge can't be coming from the water. So it has to be coming from the iron. And so I know that the iron, I know that here I have iron 2+ in my solution. These are things you should know whether they're neutral or not. There may be a table. I think there is a table in the data book that tells you what the charges are. So chlorine and bromine, pretty self-explanatory because, you know, they form negative ions, and this is cyanide. So yeah, that's something to remember. And you can always use this to figure out what the charges are on your ion. So here I've done an example, probably a while ago. So this is platinum with 3 chloride ligands and 1 ammonia. So I've written it like this, and it's asking for what the overall charge is because it's told me that platinum's got an oxidation state of 2. And so if I start this question from the beginning, because you can already see the answers. So this is the information that's come from the question. Now, ammonia has 0 charge on it because of that table up there before. Ammonia is a neutral ligand, right? So it doesn't have any charge on it, but chlorine as chloride has a 3-. Now, I've also been told that platinum's in the 2+ state, and so I can say that it's 2+. And so if I want to figure out what the overall charge on this thing is, then I know it's 3-, and there's, oh, what the hell, it's 1-, and there's 3 of them, which makes it 3- overall, and then the platinum is 2+. And hence the overall charge is 3 - 2, which equals, what the frick, 2 - 3, which equals -1. All right, so that all makes sense. Cool. And we'll do this last page, and then I think we'll stop because I need to eat. But yeah, transition, just memorize that. You will never have to explain how or why. This is an example of it, but it doesn't even show you where the iron is in this equation. So this is just a bit of a dumb equation that's been put in, honestly. Yeah, just remember that statement. I don't even know.
Okay, I'll do that.
Okay, so I'm assuming we're keeping on going then.
Well, actually, if you need to eat, like, it's fine.
No, it's like there's 2 pages left. We can get through this now. I'll just finish it. Okay. So here we're talking about colored complexes, and this page is called causation because I think the course doesn't explain clearly enough why it happens, but you sort of need to understand why. So colored complexes, each complex will have a slightly different color. Now, there's lots of factors that affect it, which are listed here. So it's all got to do with the amount of splitting. So it's affected by 1, the identity of the metal, so what the metal is, 2, the oxidation number, and then 3 is something that's not on my page, which I'm gonna have to look at, is what the ligand is. So basically everything that's got to do with the complex ion will affect whatever the color is. Now we'll get to that afterwards, but this is to explain why it's got color in the first place and how you figure out what the color is. So for gaseous transition metal ions, all of your 3D orbitals are degenerate. Now remember we saw that word last topic, and that means that they're all the same energy. And so when I draw my 3D block, normally it would look like that because they're all the same energy. But when it's surrounded by ligands, you get two different groups. So it ends up looking like this. You have two of them in a high level and then three of them in a lower level. And essentially this split allows for electrons to jump between the levels. Now, this is an extension page. I remember Dr. Colley once took us to the moon and back because nobody understood what was going on. I don't think it's that important. I'll just explain what's actually happening. So transition metals all exhibit this property that when they're in this complex ion state, their d orbitals split. So you get a splitting of this sort of kind. And the reason that transition metals, this goes back to the definition of transition metal. It's called transition metal because it's talking about this exact property that we're going through here, which is that the electrons can transition from one level to another. Now, the only way it can do that is if there's an unfilled d orbital somewhere, right? Because if these were all filled up here, this guy can't transition anywhere. That's what the definition of a transition metal is. There's one d orbital that has an unfilled, there's one unfilled d orbital, and that's exactly so that this mechanism can occur. So what happens is if I shoot some energy at my atom, whatever it is, and this energy is in the form of light, what can happen is if it's of the correct wavelength, so it's the right energy, I can transition an electron from a lower level to a higher level, like here. Now, I don't want you to get confused with what we did in topic 2, which was to do with energy being emitted, because that's got to do with a completely different thing. That's electrons between different energy shells that are dropping. Okay, that's not what's happening here. This is orbitals. The first thing is orbitals. And the second thing is that they're absorbing energy. They're not releasing anything. So here you're absorbing a certain color of light. So say you absorb a green color. Now, when you absorb the green light, that means that you will emit. So it's not being emitted so much as it's the color that you see. So this has all just got to do with how human eyes work. So here, it's given me another example, but whatever. So here we're looking at copper sulfate. Now, copper sulfate is a substance that will absorb orange light. So if it absorbs orange light, what this remaining spectrum of colors is without the orange, to my eyeball, that looks like blue. That's what it means. So it's got nothing to do with this copper sulfate actually emitting blue light. It's not emitting blue light. Well, it is. It's emitting blue light, but it's not only emitting blue light. It's emitting everything else, but because the orange is missing, my eye interprets all the colors coming out of that thing as being predominantly blue. And so that's why you have to use your color wheel to figure out what's going to be seen. So if orange is emitted, then you would see blue. So if green was absorbed, like in this diagram here, did I say orange was emitted? If orange was absorbed, you'd see blue. If green was absorbed, then you'd see red. So that's essentially how transition metals work when they're in complexes. And here, this is basically showing if you have a metal that's not got any electrons that can transition into a higher level, like here, all of the positions are filled, you can't transition upwards, and hence you can't get any color. So copper 1+ and zinc 2+ ions in solution, they won't give you any color because there's no transitions that can occur. So the colors always occur as a result of the transition upwards from a lower d orbital to a higher d orbital because they've been split by ligands. And when that happens, the color that you observe is complementary to the color that was absorbed. That's a simplification of this entire page here. Does that all make sense?
Yep, that makes sense.
Right. And then last page is just to do with the factors that affect color. So it's these three things that will affect the amount of splitting. Because remember before I said the difference in the energy levels, which is that split. So if I say this is my lower D and this is the higher, as that split becomes bigger, then the energy difference is also bigger. And remember, if my energy difference is bigger, so if it's this difference instead of that difference, then the frequency that needs to be absorbed will have to be higher in order for that electron to be able to jump up. And hence, if it's higher, then the frequency that I see when I look at this is also going to be different. Now, the reason that it's complex, as in it's complicated how this occurs, is because of that relationship of complementariness. So I can make a direct relationship between the amount of splitting and the wavelength that's absorbed, but I can't directly link that to what I see. So the IB is never going to ask you, what color is this thing going to be? It's not going to ask you that. It's just going to ask you what possibly could affect the color of a complex ion, or it'll ask you, like, it'll give you two different complexes like these two, and then it'll say, why do they look different to each other? And then you'd have to say why. So the first thing you'd say, if the question was, why does manganese 2+ with water look different to iron 3+ with water? The first thing you can comment on is always what the metal is. So I would just say, since the metal is different, the amount of splitting that occurs is different. That's literally all you have to say. Like, there's explanation as to why certain ones will affect certain things, but then if your ligand is different, then you'll get completely different answers. So don't bother too much with understanding the theory, just remember these three statements. The next thing is the oxidation number. So I could say these would also split differently because the oxidation number is different. Here I can see that I've got a neutral ligand, so the oxidation states on water is 0, and hence for manganese, I know this has a 2+ oxidation state, and iron has a 3+ oxidation state. Since they're different, there'll be different splitting. Don't really need to understand why, just it does. Because the charge means that you've drawn your ligands in closer, so these iron ligands, the water ligands in this iron molecule are closer than the manganese ones, and so your splitting actually increases. As for how that actually affects the color, like if it turns from red to green or something, you don't need to know. But just remember, the higher the charge, the more the splitting, not the less, the more. Mm-hmm. And the last thing is what type of ligand you have. Now, it's called a spectrochemical series, and you can find this in your data booklet. It's like section 15 right there, which gives you this entire list, and it tells you how strong a ligand is, essentially. So this is saying that the further down you are here, the less splitting you cause. And so it says that iodine ions are really weak ligands, and carbon monoxide, cyanide, very strong ligands. So again, if it was asking you, like, if the ligands were different, you'd just say the nature of the ligand is different, and hence the splitting energy, so the amount of splitting that occurs is also different, and so you get different colors. Yeah, don't worry about that graph. So just remember these three things. And if her question asks you, just list them and say that's why it's different. But you don't need to explain how the color changes exactly, because you don't know. And we don't.
Okay.
But yeah, that's 3 and 13 done. Any questions?
Not really. I think it's all good.
Yeah, that's cool then. Well, that's all done then. Okie dokie.
Yep.
Yeah, we're all good. When do you want to do tomorrow? Or do you want to